In this video, I will be finding the Lagrange equation of motion for this system, which is a simple yo-yo. So in this problem, there's a cylinder here that has a string wrapped around it. And when the cylinder is released, it falls and it acquires a center of mass velocity and a angular velocity, omega. This problem comes from the book Classical Mechanics by John R. Taylor, and it's problem 7.14. In the book, they call this axis the x-axis. I don't like that, so I'm calling it the positive y-axis. So the positive y-axis is down. All right, so in order to do this, we need to find the Lagrangian. And the Lagrangian is defined as L equals T minus U, where T is the kinetic energy, U is the potential energy. So first, I need to find the kinetic energy of this system. For this yo-yo, T is equal to 1/2 mv squared plus 1/2 I omega squared. Here, V is the velocity of the center of mass. I is the moment of inertia for a uniform cylinder. And that equation can be looked up online or in a physics textbook. So for a uniform cylinder, I equals 1/2 mr squared, where r is the radius and m is the mass of the cylinder. So from looking at this problem has 1 degree of freedom. It's only free to move on the y-axis. So I'm going to pick y as my generalized coordinate, and I'm going to rewrite this in terms of y and y dot, where y is the position and y dot is the derivative of the position with respect to time. So this will be t equals 1/2 m y dot squared plus 1/2. Now I'm going to put in my equation for I times 1/2 m r squared, and omega is the angular velocity. One of the equations for angular velocity is V is equal to omega cross r. So what I'm going to do is, in order to find, I want to get rid of omega here. So I want to get this in terms of V and R. This should be a capital R. So omega is equal to V over R. So this omega is going to turn into V over R, both of those quantities squared. So now what I want to do is I want to simplify this. These R's cancel. This becomes 1/4, so this is going to equal 1/2 m y dot squared plus 1/4 m. And this will be, because remember earlier we said we're getting this in terms of y and y dot, so this v right here should be y dot squared. And we can simplify this a little more. This will be t is equal to, both terms have the same variables. 1/2 plus 1/4 is going to be 3/4. So the total kinetic energy of this system is going to be 3/4 m y dot squared. Great, so we figured out T. Now we need to figure out U. U is the potential energy. The potential energy of this system is equal to negative m gy. And there's a negative sign here because the positive y-axis is pointing down. So if there wasn't a negative here, then we would be saying that the potential energy is increasing as the object falls. But we know that as an object falls towards the Earth, its potential energy decreases. So we have to put that negative sign there. So now we can rewrite our Lagrangian as L is equal to 3/4 m y dot squared. And because it's t minus u, and u is negative, this will become plus mgy. So now we need to determine the Lagrange equation of motion. The Lagrange equation of motion states that the derivative of the Lagrangian with respect to your generalized coordinate, in this case it's y. This is actually the partial derivative with respect to y, minus the derivative with respect to time of the partial with respect to y dot is equal to 0. So now I have to find the partial derivative of this equation with respect to y. The only y term in this equation is here. So this will become L is equal to mg. The partial of L with respect to y is equal to mg. Now I need to find the partial of L with respect to y dot. There's a y dot term here, but not here. So if I take the derivative of this with respect to y dot, that's 6/4 m y dot, which is equal to 3/2 m y dot. Now I need to take the derivative of this with respect to time. So d over dt times the partial of L with respect to y dot. That's going to be 3/2 m y double dot. So y double dot is the acceleration in the y direction. Y dot is the velocity in the y direction. So now we have the partial derivatives that we need and the derivative with respect to time of the partial with respect to y dot. So we can plug this equation and this equation into this equation. So that's going to be mg minus 3/2 m y double dot equals 0. So we need to solve this for y double dot. That's going to be 3/2 m y double dot equals mg. There's an m on both sides of the equation, so those cancel out. Multiply both sides by 2, divide each side by 3. So y double dot is equal to 2/3 g. This is an equation of motion showing that the cylinder is accelerating downward with a value of 2/3 g. where g is the gravitational acceleration close to or near the Earth's surface.